Yeah, but it's purple. Oh, are we ready? Okay, sorry. All right, we are now ready to begin our next chapter, chapter 12. So let's talk about chemical reactions. Chemical reactions, we know so far in last semester chemistry and so far this semester chemistry, we know that chemical reactions, many of them go to completion. And by completion, we mean until at least the limiting reactant is consumed, disappears. So go to completion means until one or more reactants are completely gone, transformed into products, is completely consumed. So we even write reactants transform into products. That's how we write our chemical equations. And so if we take a look at something like this, we have a couple of ions here that we can use to mix together to produce nitrogen gas and some hydroxide and other ions. You carried out this reaction sequence in a couple of your lab experiments when you were synthesizing nitrogen gas. And in this reaction, we know we can do things like measure the volume of the gas produced. We assume that reaction, we get it going, we go to completion, use up that limiting reactant, and we get that nitrogen. We collect it and make it push water, if we can measure the volume of the gas. We can also do things like calculate the theoretical yield of any of these products, the nitrogen or any of the ions. We can calculate or measure the heat of the overall reaction when it completes. Oh, yeah. And oh my gosh, we can even follow kinetics. We can gather kinetics data to determine the rate law of the reaction and more data to help us determine the activation energy of this reaction. We got lots of skills. We know how to analyze chemical reactions that go to completion. I want to slow down a little bit. Yeah, I'm saying many chemical reactions go to completion, but we have to realize that most chemical reactions do not go to completion. What? Does that mean we just like stop them after 8.5 seconds or something? No, we're actually talking about reactions that just don't go to completion. They can't. And instead, what happens is the chemical change results in, yeah, you get some products, you get some reaction, but you also still have reactants in there. You end up with a mixture. And it's a very special mixture. It's a stable mixture. That mixture will not result in any more product, and it still has reactants in there. This is weird. But most chemical reactions do not go to completion. So it must be a pretty important idea. So do not go to completion means it can't. So instead, we got a mixture of products and each of the reactants. So to study this, we want to take a look at this reaction here. We'll just envision the gas phase, nice and simple. You already synthesized this gas, nitrogen dioxide. You know it's a brown gas. And it turns out that if two of these react, if they collide with each other, they can join up. They can become a dimer. They can join up to become N2O4, which is a colorless gas. It has no color. So we start with some dark brown. If we got a mixture of a whole bunch of these NO2s, we'd have a dark brown mixture, a bottle of brown gas. And if it reacts, then it should be producing some of this colorless, right? So some of the dark brown color should go away and we start getting no color. Now, it turns out the forward reaction here, the activation energy, is less than 50 kilojoules. So if we start with NO2, the high point here, we go, it's less than 50 kilojoules, which we know is an activation energy that's pretty easy. This reaction goes pretty easy at room temperature. Now, the delta H for the reaction shows a negative 57. So that's exothermic, and okay, simple pathway, easy reaction. So what happens if we place the whole bunch of this NO2 gas, brown gas, a certain amount of pressure that it would exert in a container and we just leave it there under room temperature conditions, we know there's going to be some reaction. So we just leave it undisturbed. And what do we observe over time? Well, over time, what happens is we start with our dark brown, and then there's reaction because the activation energy is so low, it goes lighter. And then after a while, there's some point in time, I mean, we don't disturb anything, but there's some point in time where it doesn't go completely colorless. It actually stays light brown. What? Why doesn't it go completely colorless? I guess this is one of these reactions that does not go to completion. It remains light brown. The experimental evidence means there's still some color in there. Certainly there's some reaction. Some of the dark stuff disappeared. So that means we got some colorless stuff in there, but it's still light brown. So we want to analyze that. The color stops changing. So maybe taking a look at this graph, we start thinking about, okay, we start with our reactant. What's this graph? This is pressure versus time. So pressure versus time, well, oh, this looks like a kinetics graph. If we were to gather data, we start with reactant and we don't have any product. So we start with reactant, and over time, that decreases. So the pressure it exerts is less and less. And then over time, oh, this is the product curve that starts at 0, and then that increases. So that's what it's saying over time, right? So the dark brown stuff starts disappearing. We start getting colorless stuff. So overall, this mixture is light brown. But then after some point in time, look at this, how these curves level off. At some point in time, the color stops changing. There's still some color. It's light brown. So if I continue the time frames, and I'll try to do it on my graph, this just levels off. And this just levels. No more change. A lot of change happens in the beginning of a reaction, but after a while, no more change. Color stops changing. We got a mixture. We got some brown stuff, not much, and some colorless stuff. So we end up with at some point in time, a mixture of reactant and product. And then because these curves are leveling off, there's no more change in the total amount of the reactant. That becomes constant, and we could measure it. And no more change in the total amount of product. That's constant, and we could measure that. So is there any change? Like maybe this starts leveling off, maybe right about this point in time. Is there any change occurring at that point? I mean, there's no change in the amounts of reactants and products because we have no more color change. So there's no change in the total amounts of things. But is there any change occurring? I mean, we are talking about a sample of gases, and we know a lot about how gases behave. Gases move in continuous motion. There's lots of collisions happening in this container. So there's still ongoing collisions, and the activation energy is pretty low. So that means since there's NO2 in there, they could still collide successfully to form some product. Some reactant can form product if there's collisions. So I guess we have to start saying, well, maybe this reaction is reversible. Maybe it's reversible if we take a look at this graph again and we try to look backwards. Here's some product trying to become reactant, the activation energy there. Well, that amount of energy, that's still something right around 100 kilojoules. It's still reasonable that could happen under room conditions. So we've got N2O4 breaking apart into two little NO2s. We've got a reversible process. It has to be. And not only that, but when these amounts level off, this point in time, it's ongoing collisions. There's some dynamics going on, some change, but yet no change in the total amount. So it has to be that because this is a reversible reaction, the point at which the product decomposes is happening just as fast as the product is formed. So if if some of this product splits apart to become reactant, then some of the reactant's going to get together and form the product again. I mean, we got some ongoing collisions, but overall, we remain the same amounts of reactants and products. So it's at this point in time when there's no more change in the total amounts, yet there's ongoing collisions. At that point in time, we want to say we have a dynamic balance point. We want to say that the chemical reaction has reached the state of equilibrium. And we use these double arrows to represent this state of equilibrium, double arrows. The state of equilibrium, ongoing reactions, but overall, there's no net change in the amount of product versus the amount of reactants. No net change. Let's think about that a little bit more in the next video.